What I'm going to show you now is a way to get coefficients for some partial fraction decompositions, but you need to have distinct linear factors. And so this method is attributed to an electrical engineer, Heaviside. So the Heaviside method when it comes to partial fractions decomposition. And this is a sad story. Heaviside had all these great techniques he used, particularly with these differential equations. If you take differential equations at the end of the course, you'll see why Heaviside was involved with all this stuff. Because circuit analysis. Circuit analysis requires a reasonable amount of partial fraction decompositions to help us solve diff-EQs. And I guess apparently at the time, the mathematicians, they poo-pooed it. Okay, Brad, have a good day. They unfortunately poo-pooed it, and then eventually the mathematicians, after Heaviside died, they came back and said, okay, well, this is actually all legit. So here's how this goes. What we need for this to work is distinct linear factors. Excuse me. Here's how this works. Let's say you're trying to partial fraction decomposition this. All right. All right, well, you would have the basic form a over x minus 2 plus b over 2x plus 1. All right, now if you're doing what we did today, we would multiply both sides by that common denominator. Certain things would cancel, other things would stick around, and then we would try to cheese the answers by plugging in values that make those factors 0. So all this method is it's doing that same thing without writing out all the steps. So here's what you do. Let's say you want to figure out what a is. Well, you go in here and you find out what makes that 0. What makes this 0 is x equals 2. Now, when you would multiply through by the denominator, that x minus 2 would be attached to the b. And that would be zeroing it out when I plugged in that. So plugging in x equals 2, what makes the denominator on a 0 would actually be canceling out the b term on the other one. So then what you do is you go over here and you cover up the x minus 2, pretend it's not there, and plug 2 into the rest of it. Boom, a is 4/5. And that's say you wanted to get b then. Well, now you do the same thing with b. You go over to b. You find out what's going to make that 0. Negative 1/2. And then you come over here and you cover up the 2x minus 2x plus 1 and plug negative 1/2 into the rest of it. So you have there in the numerator, you got negative 1 over, what, a negative 5/2? So that would be a positive 2/5. Boom, you're done. All right. Let's try another one. So sometimes this is called the Heaviside cover-up method or the Heaviside method. You need distinct linear factors. All right. Let's say you had 4 minus x over x times x minus 1 times x plus 2. So, oh, great. I got distinct linear factors. It's time for the Heaviside method. What value of x makes this denominator 0? X equals 0. So I'm going to go over here and cover up that. To get a, going to plug 0 into the rest. I get a negative 4. So a is going to be, oh, excuse me, not negative 4, negative what? Negative 2. Okay. I want to go looking for b. So what do? What value of x makes that 0? X equals 1. I'm going to go over here, cover up the x minus 1, and plug 1 into the rest of it. And I get what? 3 over 3, which is 1. What's my c? Plug the negative 2 in. Everything except that x plus 2. Numerator there, I get a positive 6. Denominator there, I get a what? Positive 6. So I get 1. Okay. Well, here, we're asked to use the Heaviside method to help you integrate the following. So we had a little intro to the Heaviside method. Works for distinct linear factors. Let's take a look at this first integral here. We've got the integral of 5 minus 5x divided by 2x squared plus 3x minus 2 dx. Okay, once again, before we jump off into partial fractions, we would try some other standard techniques. A basic u sub doesn't seem to hack it here. So we would start the partial fraction decomposition, 5 minus 5x. We try to factor the denominator. So we would need to split the 2x and the x, and we would have to figure out combinations of factors of negative 2 that when multiplied together and added would get up to a positive 3. So we could have a positive 2 times the 2x to give us the 4x, and then a minus 1 would take it back down to 3. So just quick check. There's your 2x times x, 2x squared. There's a positive 4x, a minus x to give us a 3x, and the minus 2. So following the partial fraction decomposition theorem, this is going to look like some constant a over the factor 2x minus 1 plus some constant b over the factor x plus 2. And since we have distinct linear factors, we can apply the Heaviside. All right, so how does the Heaviside method work? Well, let's go in and look at this first term here. We look at the first denominator. We set 2x minus 1 equal to 0. So we would have an x equals 1/2 come out of that. And then I come back over here. I would cover up the 2x minus 1 factor in the denominator and plug x equal 1/2 back in. So I would get a equal 5 minus 5 times 1/2 over 1/2 plus 2. So once again, I cover up the factor that would be 0 and plug the root here, x equals 1/2, into what's left over. And what do I get out of that? I get 5 minus 5/2, which is 5/2, divided by 1/2 plus 2, which is 5/2. So that's giving me a to be a positive 1. Now I go over to this linear factor here. Set this equal to 0. The root here would be x equals negative 2. I would cover up the factor there, x plus 2. Plug negative 2 into what's left over there, 5 minus 5 times negative 2, divided by 2 times negative 2 minus 1. In the numerator there, I would get a positive 15. And in the denominator, I would get a negative 5, so b would be a negative 3. And so then this tells us our partial fraction decomposition. We've got a 1 for a, so that's going to be 1. B is going to be a negative 3, and now we're all set. The integral of 5 minus 5x divided by 2x squared plus 3x minus 2 dx is the same as the integral of 1 over 2x minus 1 minus 3 over x plus 2 so we can use the sum and difference property here. 1 over 2x minus 1 dx minus 3 integral 1 over x plus 2 dx. And now we can use the principle of linear substitution here. This is going to work out to be a 1/2 natural log absolute value 2x minus 1 minus 3 natural log absolute value x plus 2 plus c. So once again, the Heaviside method is just a more efficient way. You know, it's kind of like tabular integration. It's sort of a shortcut way to get the coefficients in certain situations. Let's take a look at this next example. We're asked to integrate x squared plus 3 over x times x minus 1 times x squared plus 1. So what's nice is that denominator has already been factored for us. We can check that the x squared plus 1 is an irreducible quadratic. If we said x squared plus 1 equals 0, there's going to be no real solutions. We know that because any x value you plug in will get squared added to 1. Or you could look at it that way. So that means we're all set to begin the partial fraction decomposition. So we can have an a over x plus b over x minus 1 plus cx plus d over x squared plus 1. Now Heaviside is going to help us get the a and the b, at least, and then we'll have to get the c and the d using the traditional way. But once again, to get the a, you look at the denominator here. You set it equal to 0. You find the root there is x equals 0. We're going to cover x up and plug 0 into what's left over. Plug 0 into the numerator here. 0 squared plus 3 is 3. 0 minus 1 is negative 1. 0 squared plus 1 is 1. So we get a equals negative 3, courtesy of Heaviside. And now to get to the b, I set this denominator equal to 0. I find the root is a positive 1. So I'm going to cover up the x minus 1 factor here and plug 1 into what's left over. 1 squared plus 3 is 4 over 1 times 1 squared plus 1 is 2. So I get b equals 2, courtesy of Heaviside. So to get the c and the d, I need to clear denominators and match up coefficients. So let's do that on the next slide. X squared plus 3 equals. Multiplying through by the denominator, I'd have the a, which is negative 3. The factor of x would cancel, but the factor of x minus 1 and x squared plus 1 would remain. Plus I'd have b, which is 2. The factor x minus 1 would cancel, but the factors of x and x squared plus 1 would be the same, or would remain rather. And then I've got the cx plus the d. The x squared plus 1 would factor, or cancel, and I'd be left with the factor of x times x minus 1. Now you could go ahead and multiply everything out, or we could just sort of look at what the highest power of x is going to be coming out from the right and left hand side. On the right hand side, you notice we'd have x cubes coming out. So let's count up the x cubes on either side of the equation. Well, on the left hand side of the equation, there's no x cubes at all, so we'd have a 0 here. Now let's look at this first term here. How would I get an x cubed out? Well, let's see. I'd have a minus 3. I'd have to multiply by the x from that quantity and the x squared from that quantity. That would give me an x cubed. No other combination here of these factors would give me an x cubed. So I have minus 3x cubed coming out of the first term. From the second term, I'd have the 2, I have the x, and I'd have to multiply by the x squared to give me a positive 2x cubes out of that. And once again, there wouldn't be any other x cubes. And from the last term, I'd have to have the cx times the x times the x. That would give me cx cubes. And no other combination of these factors is going to get me up to an x cubed. So I would have minus 1 plus c is 0. So c here is positive 1. Then we look at x cubes. We're looking for d now. So if I look and see what's going to get attached to the d, I see I'm going to have a dx squared come out. So we'll look at x squareds next. I have 1x squared on the left-hand side. What would what would I multiply by here to get an x squared from this first term? Well, I'd have the minus 3 times the minus 1 times the x squared. That'd give me a 3x squared from the first term, and there'd be no other combination would give me an x squared there. The second term, you're always multiplying by 2x, so you would not be producing any x squared terms here. What about getting x squared out of this last quantity? You've got the cx times the x would give you an x squared. If I multiply that by the minus 1, that would give me a minus cx squared here, and then plus the dx squared there. So knowing that c is 1, 3 minus 1 is 2, I'd actually get 1 equals 2 plus d. So this would give me that d is minus 1. So c is positive 1, so 1x minus 1 there. And so now we're all set. The integral x squared plus 3 over x times x minus 1 times x squared plus 1 dx equals the integral of a over x, which is a negative 3 over x, so minus 3 over x, plus the b over x minus 1, but the b is 2, the cx plus the d, the cx is a 1x, so that'd be an x over x squared plus 1. And minus a 1 over x squared plus 1. Okay, so that's our partial fraction decomposition. Now we go through integrate. We get negative 3 natural log absolute value x plus 2 natural log absolute value x minus 1. Here we could do a little u sub to get a 1/2 natural log x squared plus 1. And since x squared plus 1 is always positive, we don't need the absolute values. And then this is our old friend, the inverse tangent of x plus c. So that'll do it for that example. Last example here, we're asked to integrate 2x squared minus 3x plus 2 divided by x cubed minus x squared. Okay. Once again, we would try the usual sorts of substitutions, and we would settle on looking at a partial fraction decomposition. The denominator here, x squared, can be factored out of both terms. I get x minus 1. And so we get the form of the decomposition a over x plus b over x squared plus c over x minus 1. So here we've got linear factors. We have a couple distinct linear factors, but we do have a repeated linear factor. So how does the Heaviside method work for this? Well, if we think about looking at the first two terms here, x equals 0 is a root for both of them. All right. So if we think about clearing denominators and seeing where the x squared would cancel out completely, it would cancel out completely with this term here. There would still be an x over here that would drop out. So what you do is you come over and you cover up the factor that makes that is 0 when you substitute x equals 0. That would be the entire factor of x squared. So the Heaviside method is going to help us determine the coefficient b then. Okay? because you'd have to cover up the entire x squared to avoid a 0 in the denominator. That means the Heaviside will help us figure out b. So I cover up that 0 factor. I plug 0 into everything else. The numerator gives me a 2. The denominator gives me a -1. So Heaviside gives me b is -2. Then I go over here for c. I set c equal to 0. The root here is x equals +1. And I can cover this up and plug 1 into what's left over. So Heaviside gets me b and c. So I plug in x equals 1 in the numerator. I've got a 2 minus 3 plus a 2. So that's going to be a 1 in the numerator. And then a 1 squared, which is a 1 in the denominator. So c is 1. And now, to figure out what the a is, I'm going to just clear denominators as before. Whoops. So 2x squared minus 3x plus 2 is going to be a times what? I don't know what a is. One factor of x would cancel. I'd have a factor of x and then a factor of x minus 1 remaining. b, I Heavisided b, and I found that was -2 times. For b, the x squared would cancel out. I'd be left with an x minus 1. Plus c, which I determined to be 1, times x squared. And now I can equate coefficients. If I look at the left-hand side, x squared, I've got 2 of them. Over here, I would have ax squared from the first term. Nothing would come out of here, plus 1 over there. Boom, that gives me a is 1. So that means that the integral of 2x squared minus 3x plus 2 over x cubed minus x squared dx, which was my original integral, is equal to the integral of a over x, which is 1 over x, plus b over x squared minus 2 over x squared, plus c, 1 over x minus 1 dx. So that gives me the natural log absolute value of x. The second one is a straight up power rule. That gives me plus 2 over x plus natural log absolute x minus 1 plus c. So that's kind of the third variation of the Heaviside problem. If you have repeated linear factors, Heaviside can help you find the coefficient that corresponds to the largest of those powers in the denominator. So that'll do it for this example.